Hello guys, welcome back to Maison African Motives, still on engineering science and for working on revisions on dynamics from the question paper of November 2022. We have got our question 3 on dynamics where we have got the first part 3.1, define the coefficient of friction, and that is 2 marks for that. Okay, so your definitions actually can be taken from formulas. If you understand formulas, then it's easier for us to have a definition. Remember that the coefficient of friction is simply taken from the frictional force over the normal reaction, which is the weight in this case, which is the normal reaction that is opposing to the weight. Okay, just simply the weight in this case, because this is just opposite to each other. So which is the ratio between these two? Simply our coefficient of friction in this case. So we can have this as a ratio to say that this is, all right. So let me just write this way. It is the ratio. So it is the ratio of frictional force, the ratio of frictional force to the normal reaction. All right, to the normal reaction. So that is what we have in this case. Simply like that, you've got 2 marks for defining. From the formula, you can actually define any part that you're given. All right, on 3.2, you're given a motor car which has got a mass of 3 tons is at rest at the top of incline of 1 in 30. All right, so you're given an incline of 1 in 30 in this case. All right, and we are given that, okay, the mass, which is 3.6 tons. So, like I say, the purpose of having this presentation is that sometimes our memo, they use values from old past exam papers, which they never change values. Maybe they used another value, they still keep on using these values and so forth, which is which makes things like there is an error or something. Actually, this is the most important part. That's why we have to bring these memos to you, so that we discuss together as a family. We know what's happening. How do we answer these typical questions? All right. So let's just take our information here. We're given the mass of the car, which is it a car? Yes, the motor car of 3.6 tons. So I'm just gonna have my information here so that we do not waste much of your time, guys. All right. So the mass, that is 3.6 tons. Remember, in a ton, we have got 1,000 kgs or 1,000 kilograms. So if we multiply this by 1,000, we are going to have 3,600 kgs, given an incline in this case of 1 in 30. All right, so I'm just gonna have this. And also, we are given the length of the incline, that is 42 meters. The frictional force of 200 is constant, that is uniform. All right, the brakes are released and the car moves downwards due to the gravitational force and then onto the horizontal road. All right, so we have got the length of the incline in this case, which I'm just going to write this as S, which is 42 meters. And also we are given the frictional force of 200 Newton, which is a constant throughout. It is uniform. All right. So if we are to represent this, because this is an incline, after that it has to go to the horizontal. So which means we are going to have the horizontal at the end. It is going to be considered in the horizontal in this case. All right. So this is what we are going to have. All right. So our object is actually directly from the top of the incline in this case. All right. So this is where we have our object at the top of the incline going downwards. Then from this point, it is going to go into the horizontal. That means from this point, it has a certain velocity. Then when it reaches this with its final velocity from the incline, it is going to take that velocity to be its initial velocity now on the ground. All right. Then also we are given the distance. The distance that we are given, the 42 meter, is this in between here. So this is our 42 meters. And we have got also the incline of 1 in 30. So this is 1 in 30. So what I need you guys to understand is that whenever you are given an incline, the tan of theta and the sine of theta, they approximate to each other when theta is small. When theta is small, this is what happens. That sine of theta, it approximates to the tan of theta. So where there is a need for you to apply the tan of theta, which is equivalent to the angle, which is equivalent to the incline of 1 in 30, we can approximate that to the sine of theta also. This is what is important that you are supposed to understand. Yes, you can use the angle as it is, but there's no need for even you to calculate this angle, because these two approximately, they are the same. Not to say they are equal, it approximately equal to that one. So there is no need for you to convert. Yes, you can convert, but is no need for that. All right, so let's have our question in this case. The first part we are given, so this is just a diagram. The first part we are given to calculate the velocity of the car at the bottom of the incline. At the bottom, take note, we are still from the incline, but now we are just at the bottom, but working from the incline, meaning to say we need the velocity, the final velocity from the incline that is at the end at this point. That is the one that we need in this case. How can we obtain this? From which point or from which part? Okay. If we are to consider what we have initially from this point, we are saying we have got a velocity of 0 meters per second. So this is 3. Let me write this as 3.21, 3.21. All right. So initially, we are having a velocity of 0 meters per second in this case, or if this velocity is 0 meters per second. Then the final, so let me also indicate this, we are on the incline. So we are representing, or we are working from the incline. The final velocity is the one that we are supposed to calculate at this point, which is equal to the initial velocity for the horizontal. This final velocity is equal to the initial for the horizontal. But for the incline, we are starting from this point where we said we are starting from 0. We do not know the final, but we are given the distance in between of 42 meters. So we've got S, which is 42 meters in this case. All right. Whereby we can actually calculate this from this information. If we are to consider this formula to say that V squared is actually equal to U squared plus 2AS. We need to calculate this V, so we can simply introduce the square root. But the problem is we do not have the acceleration. So that means we are limited from this information that we have. Where can we obtain the acceleration? All right, let's consider this from the acceleration that we are given here from FA and the given forces that we are given. Remember, we've got the frictional force in this case, and we also have Fs, which is the force due to the what? Due to gravity. So which means that Fs can be obtained from this information, or I mean Fa, which is equivalent to Fs minus the frictional force. All right, where are we taking this from? Fa representing the force due to acceleration in this case. So this is going to be from mass times acceleration. Then Fs due to the gravity. This is going to be mg sine of theta. That is the parallel component in this case. The parallel component opposes with the frictional force. We are going to subtract the frictional force in this case, the one that you are given, the frictional force on this point. So in this case, what we need is to calculate the acceleration. So that means we can play with this formula here to calculate our acceleration. By dividing by the mass both sides, we can calculate our acceleration. So if we divide by mass both sides, we have our acceleration, which is going to be mg, the sine of theta, minus the frictional force over the mass. Whereby mg, the gravitational acceleration, remember, is equivalent to 9.8 meters per square second. And like I said, the sine of theta approximates to the tan of theta. So in place of sine of theta, we can use 1/30, because tan and sine approximates to each other. They are actually the same, approximately the same. So we can use 1/30 in place of sine theta. We can use 1/30 in place of tan theta only when theta is small. All right. So that is the consideration that you're going to have. So in this case, I'm just going to substitute the values that I'm having in this case. That is, acceleration is equal to the mass, where we converted our mass to kgs. We got 3,600 kgs. Take note, it was 3.6 times, so it's going to be 3,600 times the gravitational acceleration of 9.8 times the sine of theta, where we said sine of theta approximates to tan, so it approximates to 1/30. Minus, you can calculate the angle, it's fine. Then you use sine of that angle. Still, you're going to obtain an approximate answer like the one that you're going to have. Okay, the frictional force is already given, so you can just take our frictional force, which is 200 Newton in this case. So this is going to be minus 200 everything over the mass being 3,600 kgs. So this is going to give us acceleration in meters per square second in this case, or you can simplify from each part depending with what you want in this case. All right. So if you're to have this, you're going to have 0.271 meters per square second as our acceleration. This is for the inclined part that we are dealing with in this case here. Remember, we are working from the incline. So we have calculated our acceleration in this case, which is 0.271. So we are going to use this now to calculate our final velocity in this case, which is v. So we said we have got acceleration. So our acceleration is 0.271 meters per square second. All right. So to calculate v, we can just substitute our values, or here we can introduce the square root to calculate v direct. We can introduce the square root, meaning to say the v is going to be the square root of u squared plus 2as. So that is v is equal to the square root of u squared, our initial velocity of 0 meters per second. So that's 0 squared plus 2 times the acceleration of 0.271 times the displacement, I mean the speed, the distance that you're given of 42. So this is 42 meters. That is depending, we are dealing with the incline from the incline part that you're given. So this is going to give us the velocity in this case at the, which is our final velocity, that's v, or you can write as vf. All right, so the velocity is going to be 4.7. This is going to be 4.771 in meters per second. So remember this, we are talking about the final velocity that is on the incline, the final velocity on the incline, which is equal to the initial velocity on the horizontal. Remember what I was representing here to say the final velocity that we get is going to be equivalent to the initial velocity here on this part. All right. Okay, let's just hope this is not gonna affect us in our calculations here. So this part of the final velocity is going to be equal to the initial velocity that is on the horizontal. So this is what you're supposed to be very, very careful about. All right. So let's check what we are given on the other part of the question. We are now given this time the applied force. Take note, this is not just applied force, but now it's on the horizontal rod. We are now dealing with the horizontal rod. So what do we have on the horizontal rod? Remember that we are given there is a frictional force here, which is constant, which is uniform throughout. This one, it's uniform, that is being constant throughout. So meaning to say on the ground, from this point now, when you are dealing with the horizontal ground, the only force that is going to oppose as it is going this direction is the frictional force opposing in the other direction. So that is what you're going to have in this case. So that means in this case, our force in this case is going to be the negative of the frictional force. Remember, it is opposed by this force. So this is going to be 3.22 negative of the frictional force. This is the only force affecting on the horizontal. So our force is going to be equivalent to negative 200. Remember, our frictional force was 200 Newton. So that is what you're going to have in this case. All right. So that was 3.22. All right. On 3.23, we are now given to calculate the distance when the where the car will come to rest. We are dealing with the horizontal road when it is going to come to rest. If it continues to travel the horizontal. Okay, take note, guys, what I've been saying about the horizontal, to say the final velocity on the incline is equal to the initial velocity on the horizontal road. So we are going to take this final velocity on the incline, which is 4 comma. So this is on the horizontal. So for 3.23. So on the horizontal. All right. So on the horizontal, so far, this is what we have. The final velocity from the incline is equal to u of the horizontal. So meaning to say our u, the initial velocity, we have it, which is 4,771 meters per second. The velocity that it approaches the horizontal ground is the one that it is going to start from. So that's its initial velocity on the horizontal ground. But we are given to calculate now the distance that is going to be taken, or the displacement when it is going to rest. Take note here, it is when it will come to rest, the distance when it will come to rest. Meaning to say at rest, we do not have, there's no movement at rest. So our final velocity, we know that our final velocity there is going to be 0 meters per second when it at rest. All right, so at rest, that's 0. But with this information alone, we can't calculate the distance because we do not have the time that was taken for the horizontal. We do not have acceleration that was taken for the horizontal. So what can we do? Remember that we have the force when it is on the horizontal. This is the force when it is on the horizontal ground, where we say the only force that is going to affect is the frictional force. So meaning to say, from the horizontal force that we are given in this case, that we are given as negative 200 Newton, we are going to calculate the acceleration from there. Since this motor car that we are given is only affected by this force, so how it is going to be accelerating? Actually, it's a negative, which means it's now decelerating. So what is going to be the deceleration of this force that we are given, which is the only force that is now acting? Remember, previously on the incline, we were having a lot of forces here. The car is going downwards, but there is a frictional force going this way. We also have the part of the gravity, the normal reaction part. So meaning to say, we are going to consider our FA being affected by these two. But now our force is no longer affected by these two. It is only affected by the frictional force, because we are told that the frictional force is constant. So if it is constant, that is the only part that is going to affect us. So remember that our FA is going to be equivalent to F, which is equivalent to minus 200 Newton. So that means FA, meaning mass times acceleration, is going to be equivalent to minus 200. So we have got the mass of the car. The mass does not change. Whether the car is on the incline or it's down the incline, its mass does not change. The mass is still at 3,600 kgs times the acceleration. So we can calculate, in this case, our acceleration, which is the deceleration in this case. Divide by 3,600 both sides. This is going to give us the acceleration on the horizontal. So our A is going to give us a negative. So this is going to be negative 1/18. All right, negative 1/18 meters per square second, representing the acceleration, which is deceleration. All right, so like we have now, we've got our A being negative 1/18, or you can have it as a decimal, it's still one and the same thing. So which formula are we going to use to calculate S from this information? We've got U, we've got V, we've got A. Remember that S can be taken from this formula. S is equivalent to V squared minus U squared over 2A in this case, which is 2 times acceleration, where U is the initial velocity, V is the final velocity. So S is equal to V, our final velocity, that is 0 squared minus U, which is our initial velocity on the horizontal, which is the final velocity from the incline. That was 4,771 squared. Everything over 2 times the acceleration, which is in this case, it's a deceleration. That's a negative 1/18. All right, so this is going to give us the total displacement, which is 204,862 in meters in this case. All right, so this is what we were given in this case. So that is for the horizontal, that is going to be our distance on the horizontal. So the only part that was affecting was the force of the frictional force of 200, and that gives us the acceleration with the final velocity of 0 meters per second. Because it is at rest, we can calculate S, which is the distance. All right, so that was our question 3.23. We move on to question 3.3, where we are now given. All right, so let me try to shift this a little bit. All right, so let me remove this. All right, so 3.3, we are now given to calculate the average power exerted by an engine if it can lift a mass of 300 kgs through a distance of 10 meters in 2 minutes. All right, so let's take the information here. We have got, or we need the power, so that's 3.3. So we do not know the power, but we are given the mass that it is going to, the engine is going to lift an object that has got a mass of 300 kgs for a distance of 10 meters, which is S, or you can write this as the height or whatever that you have, of 10 meters in 2 minutes. So that is the time frame of 2 minutes in this case. All right. So remember that power can be taken from the work done. Remember, power is from work over time, work done over time. So whereby the work done is or can be calculated from W is equivalent to the force times the distance, or the force times the height in this case, whereby the force is mg, that is weight, times the height in this case. So we can calculate our work done. That is a mass of 300 times the gravitational acceleration of 9,8 times the height, which is the distance of 10 meters. This is going to give us the work, or the work done in joules in this case. All right, so this is going to be something like 29,400 joules in this case. So from this, we can use the formula, having our work done in joules and our time in seconds. That's power in joules per second is equivalent to power in watts. So we are going to have our power from there, work done of 29,400 divided by the time in seconds, so that we obtain the joule per second concept. All right, so this is going to be in seconds. The minute is going to be 2 by 60. Remember, in a minute we have got 60 seconds, so we can multiply by 60. So this is going to give us power measured in watts. So that is going to be 245 joules per second. So these are joules, these are seconds, which simply means 245 watts. All right, so that is how we could have calculated the power from the given information that we are given in this case, from the engine that we had. So these are the typical questions that you might have if you're dealing with the dynamics. So all you need is to work with more question papers, more revisions from our textbooks to relate information that you're given and how do you answer these questions, because how we answer question papers is very, very important. So the more we revise question papers, the more we understand or know how do they want us to attempt such typical questions that we be given. For now, guys, that's it from Maison African Motives, working on Science N4. Till we meet again.